very much. Next, we will have Stuart Marongwe, who will give us a talk about impossible galaxies, Hubble tension, and the Ritchie-Soliton miracle. Stuart has graduated from the University of Jose Barona in Cuba, getting a licentiate degree in physics and electronics. And he later went to Bust to get his MSc, and currently he's pursuing his PhD in theoretical physics in the University of Botswana. His research interests are quantum gravity and its applications in astrophysics, condensed matter, and technology in general. He has written a number of papers, and today's talk is on one of the papers. Without further ado, Mr. Marongwe, if you are ready, please indulge us.
Thank you very much, Dr. Tsipa, for that kind introduction. I take it that everyone participating in this presentation is very much interested in astrophysics or astronomy or both. So my presentation today is about one of the cosmic mysteries, especially at cosmological level. But my screen is not moving now. Okay, now I'm testing it, it's moving. All right. So like Dr. Tsipa introduced, my topic is impossible galaxies, the Hubble tension, and the Ritchie-Soliton miracle. So it's based on this equation you can see. And so this is how my talk is going to proceed. I will introduce the standard model of cosmology, or lambda CDM. I will introduce the problem of impossible galaxies and some proposed solutions. Then I will introduce the Hubble tension, which is one significant tension in cosmology, although there's another one called the SA tension that is kind of related to the Hubble tension. I will also briefly discuss it. Then I will introduce the Ritchie-Soliton and how it solves this problem, and also present some supporting evidence to this solution. So let me introduce, first of all, the standard model of cosmology. The standard model of cosmology is based on general relativity, which we all know is Einstein's theory of gravity, and a cosmological constant, or what most of us know as dark energy, and it includes another substance called dark matter. So if you look at this equation, G mu nu lambda G mu nu, that's the equation that governs our current knowledge of cosmology, where that upside down V is the lambda that represents dark energy, and that big X or chi represents dark matter density, the stress momentum tensor for dark matter. T mu nu, that big T, is the stress momentum tensor for the matter that we are all familiar with, stars, light, and everything like that. The reason why there's that chi, or dark matter, is because stars at the edge of galaxies do not obey what we call Keplerian dynamics. What is Keplerian dynamics? Keplerian dynamics is observation of rotation of planets in our solar system. For centuries, people like Tycho Brahe and Nicholas Copernicus and other ancient astronomers were observing the motion of planets. They could tell, especially after Tycho Brahe's measurements and Kepler, subsequent Kepler, that Mercury moves faster, closer to the sun. Venus, even slower, Earth slower, and ultimately Pluto will be the slowest planet rotating around the sun. So this is called Keplerian dynamics. But when it comes to galaxies, you will find that the outer stars at the edges of the galaxies are rotating at the same speed as those near to the center of the galaxy, which is quite obviously, blatantly disobeying Keplerian dynamics. So this is what you call standard Newtonian dynamics. So to explain this mystery, astrophysicists and cosmologists postulated the existence of some dark matter, first done by the Swiss-American astronomer Fritz Zwicky. He proposed that there is some dark matter because he had observed this phenomenon in amongst galaxies, the Coma cluster especially. He found that using the observed matter around the Coma cluster, the galaxies in that cluster were rotating about each other faster than the matter that is in that cluster. So he proposed some invisible matter called dark matter. Later in the late 70s, Vera Rubin discovered that stars in the galaxies also do obey this non-Keplerian dynamics, in which we find that stars at the edge of the galaxies are rotating almost as fast as the stars next to the center of the galaxy. So they also propose some dark matter within galaxies in order to compensate for this extra gravity, because without this extra gravity, these stars would fly off from the galaxy. So there's this substance which we call dark matter, which is supposed to hold stars together. To explain the observed phenomenon, we call it dark matter. So there are a lot of wild theories on what is causing this dark matter. Some are postulating some exotic particles that are not in the standard model of particle physics. Some are postulating the modification of the laws of gravity themselves at large scales. So you will see in this presentation where I stand. So far I'm saying our model of cosmology includes dark energy. So what would be dark energy? Dark energy is a proposed form of energy that affects the universe at large scales. So how was dark energy discovered? In 1998, two groups of astronomers set out to measure the expansion rate of the universe. They intended to measure the Hubble constant, and they expected to find that the universe, as it is aging, should slow down, then suddenly reverse back and collapse on itself. But what they discovered was something surprising. Instead, they found that the universe was beginning to accelerate faster and faster. Something must be driving this accelerated expansion of the universe. So they call this energy that is driving the universe dark energy. It is so surprising from a physics perspective. It's like throwing an apple into the sky and obviously expecting it to fall back. But in this scenario, it's like the apple is beginning to move faster and faster, escaping away from the earth. So there must be some energy driving it. And the source of this energy is unknown. That's why it's called dark energy. Its properties, that is why there's a lot of astronomical surveys to try to understand its properties and how it evolves in cosmic time. Currently, in the lambda CDM model, dark energy is considered as some energy in the background of space that is always constant and driving the accelerated expansion of the universe. But latest results are beginning to show that this dark energy seems to be decaying. It seems to be losing energy. It seems to evolve with time. So another mystery, apart from dark matter mystery, apart from dark energy mysteries, there is this thing called the impossible galaxies. What has happened in the past 3 years? We have the astrophysical community and the cosmological community have witnessed some unprecedented discovery in cosmology that they're usually called universe shakers because of the JWST telescope. This telescope observes in the infrared, so it can go beyond the current Hubble telescope that observes primarily in the visible light. So the JWST can go deeper into the universe and see galaxies at the dawn of time itself. So what has JWST observed? In theory, astronomers expected to see infant galaxies that are trying to merge and form bigger galaxies. But what JWST has observed is something not short of a miracle. It's seeing old galaxies that are mature, some that have their stars extinguished, like some even high metallicity. High metallicity means that these stars, they are stars that have exploded. They've grown and exploded, aged, and let out some dust into their environment. And this, we are talking about 300 million years into the birth of, after the Big Bang. So it's like going to a kindergarten class or school, expecting to see toddlers. Then you start seeing 8-year-old in the classroom. So this is totally surprising. That's why it's called impossible galaxies. And the other thing about these impossible galaxies, in order to be as bright as they are, they need to have transformed all the hydrogen gas in the early universe, 100% converted into stars, which is not physically possible given the short time in the early universe, 300 million years. You can't see this type of galaxies. So what are the suggested solutions to this problem? Some are saying maybe our measurements of the distance of these galaxies is wrong, but this has been verified and they found that the redshift or they are as far as JWSTs, like nearly 13 something billion years ago in time, in terms of time. So they're also trying to bring out concepts like clustering physics, in which dark matter halos collapse earlier than allowed by current models. This is possible in the presence of dark energy, but the physics from Planck satellite are showing that cannot happen. Something mysterious is happening at the dawn of time, where we find galaxies that are too mature for their time. Like, as I said before, like finding old people in a kindergarten class where you're expecting to see toddlers. So there's this other thing called Hubble tension. So what is the Hubble tension? In short, I can say there's this Planck satellite. It uses the cosmic microwave background to map the parameters of the universe. So it can use these parameters to then extrapolate on how the universe currently should behave. So it can compute the Hubble constant at this age of the universe, starting from those parameters it has obtained from the early universe. So according to Planck, to the Planck observation, which are highly accurate, and other early universe observations, the Hubble tension is supposed, the Hubble constant is supposed to be around 68 kilometers per second per megasec per sec, which means after a million, a parsec is like 3 light years. A megaparsec would be like 3 million light years and above, 3.6 million light years. So what it means that if I have a Hubble constant of 68 kilometers per second per megaparsec, it means after that that distance, the galaxy expands at an extra 68 kilometers per second. Galaxies beyond that, after every 3 million light years, you'll find that each galaxy will be moving faster by 68 kilometers per second. So current measurements show that no, that speed should be 70 to 75 kilometers per second. They thought, first of all, it was systematics. Maybe we are measuring, as you can see in this graph to your right, maybe we are measuring, our instruments are not fine enough. But now the instruments are fine enough. They can clearly distinguish the early universe measurements for the Hubble constants are different from the late universe measurements for the Hubble constant. So the Hubble constant currently in this time of our universe is currently around between 70 to 74 kilometers per second per megaparsec. But if we extrapolate from the early universe, it's supposed to be 68 or 69 kilometers per second. So this is what is known as the Hubble tension. Apart, like I mentioned before, apart from the Hubble tension, there's what's called the S8 tension. It means the S8 tension is another tension in which the lambda CDM, that is the current standard model of cosmology, based on these Planck observations, is showing that the universe is not as expanded as it should have been. There's actually, like, it's being arrested in these late times. It's not expanding as fast as it should be expected under a constant cosmological constant. It seems to be expanding under the influence of a varying cosmological constant instead. So far, they've ruled out that it's not measurement problem. So there's some new physics that is taking place, and these are the mysteries that are keeping most cosmologists and astrophysicists awake at night. Okay. So what are the proposed, like I said, the proposed solution to the Hubble constants are, is my slide moving there? Hello?
No, it's not moving.
Okay, now it's moved.
Okay, now it moved.
Okay, so these are the proposed Hubble tension. One method to resolve these disagreements between conflicting data is to make measurements that are both precise and accurate. These methods include taking measurements of stars from distant galaxies as well as gravitational waves to improve quality of the data. So here they are trying to introduce multi-messenger astronomy to get precise distances of these galaxies, and so that there's no conflict between early measurements and late time measurements of the Hubble constant. However, there's these shoes led by Adam Rees and others demonstrate high precision and consistency of the data that currently stand at 4 to 6 sigma statistical significance, meaning that this agreement between these two types of measurement is real. It needs some explanations in terms of modification to lambda CDM itself, that is the standard model, or some new physics. So here we now introduce what is known as the Ricci soliton. Okay, the Ricci soliton first appeared in my equations of quantum gravity. So in recent times, over the past 2 years, I've been trying to translate my quantum gravity theory into a classical form, So in order to do that, I had to use what is known as Mach's principle. Mach's principle, in its vanilla form, or in its other flavor form, sorry, it says that space-time cannot exist without matter. Okay, so what Einstein's equations do, they just show how matter moves in, how space-time curves in the presence of matter, and how matter moves in the presence of curved space-time. But Mach's principle adds another thing, that space-time itself cannot exist in the absence of matter. So I included this part here in Einstein's field equation. So what is a Ricci soliton? A Ricci soliton is a compact Einstein manifold. When I say compact Einstein manifold, imagine this bubble that surrounds this galaxy. This bubble is generated from the presence of gravitational energy. The gravitational energy itself around this galaxy generates this bubble, or this. So apart from curvature of space-time, by the presence of matter itself generates a Ricci soliton, or the gravitational energy density. Basically, it's sourced from the gravity generated by matter. So you will find that there's a bubble that surrounds any form of matter, be it an atom, but then it becomes so apparent at large scales, at large quantities of matter. That's when the Ricci soliton becomes very apparent. And this is what we are interpreting as a dark matter. So I include the Ricci soliton The Ricci soliton is this part, sorry, K minus K G mu nu. And this is the usual Einstein constant. And this tau mu nu is gravitational energy density that sources this Ricci soliton. So once I include this equation into Einstein, the Ricci soliton into Einstein's field equations, we end up having this last equation here, G mu nu plus lambda prime. So in my work, in my research, the universe is governed by this. It's similar to Einstein, but the difference is the primes. This prime shows that there's a varying cosmological constant. This T prime, the stress momentum, it shows that there's some, I've separated gravity from pure matter, and then there's some gravitational energy. Some of this gravitational energy came from the Big Bang, from the gravitational waves of the Big Bang. That is independent of matter. And this gravitational energy density is what generates compact Einstein manifolds, or these Ricci soliton, and then we interpret it as dark matter. So this modifies, and there's a lot of things that it helps with general, just by including the Ricci soliton. We solve in general relativity itself. Energy and momentum is not conserved, but if I include this Ricci soliton, energy and momentum is conserved. It also satisfies Lovelock's theorem. It's a theorem that governs equations of gravity in four-dimensional space. As you can see, the equation here, this equation, it still appears like Einstein's equation, so it satisfies Lovelock's theorem. But I have also an interpretation, just like Dr. Tsipa has said, that I work on quantum gravity, where you can interpret this Ricci soliton from a quantum gravity perspective. It's just a ball of gravitonium, like gravitons that are glued to each other to form a ball. In the nucleus, the force that creates interaction between quarks this force is mediated by particles called gluons. These gluons can attract each other and form a ball called gluonium. In the same case, gravitons can attract each other and form a ball called gravitonium. And this is the Ricci soliton, which we are calling gravitonium. And the Ricci soliton is also something that has been mathematically studied in differential geometry. It has three states. It's either it's a steady soliton, or it's an expanding or a contracting soliton. So in this case, this one expands with time in these modified equations. So this is what I was saying about the gravitonium bound state. So what we are seeing, these blue curves are high energy gravitons that form the bond state, and then decay slowly by emitting these red low energy gravitons. This also explains why gravity is not a strong force, because the high energy gravitons have been bonded. Only the weak ones can escape. This makes gravity a weak force. It's also known as the hierarchy problem, because gravity is so much weaker than any other of the all four fundamental forces. Gravity is so weak. It is not comparable to the other three forces: electromagnetism, weak nuclear, and strong nuclear force. So this is the reason why gravity loses strength, because the strong gravitons themselves are bonding to form a gravitonium bound state. And this bond state is the dark matter that we are seeing. So what are the supporting evidence? If I put gravitonium and try in this form, like this is gravitonium, and I try to interpret the galaxy rotation curves, I find that they are in agreement with what is observed. And the density of dark matter to light matter is approximately what is observed, just from including the Ricci soliton into Einstein's field equations. I also derived this part of this equation has been derived empirically. It's called the Baronic-Tully-Fisher relationship. No one can derive it from principles. Other models cannot derive it from first principles. But including the Ricci soliton, you can derive it. But in the Ritchie-Solerton model, where the Ritchie-Solerton is included, there is this factor that expands the Ritchie-Solerton with cosmic time. It's called, so this baronic-Talley-Fisher relationship now becomes the evolving baronic-Talley-Fisher relationship. And it has been observed, you can observe that older galaxies rotate faster for the same amount of mass than young galaxies, all because of this term here, the evolving baronic Talley-Fisher. So this is graphs showing the blue galaxies are the younger galaxies, the red ones are the older galaxies. They will rotate faster for the same given mass than a younger galaxy. So if everything has to do with physics, then this is the term that is causing the older galaxies to rotate faster. This expanding Ritchie-Solerton term that is time dependent. Also, there's this, they have noticed that galaxies begin to rotate at the same speed after the acceleration around the center of the galaxy reaches this small value, 1.1 times 10 to the power minus 10 meters per second squared. This is derived empirically from the Ritchie-Solerton hypothesis. It's derived, whereas in most models it's included because it's made from observations. And there's this mysterious galaxy called the Horrocks object. It's like something from science fiction. No one knows how it has been formed. But if you include the Ritchie-Solerton, it will model it. This is actually a picture of a Ritchie-Solerton in principle. In the Ritchie-Solerton, you'll find that at the edge of the Ritchie-Solerton, these time moves, the clocks at this edge of the Ritchie-Solerton, they are slow. The clock moves slowly. But where there's a lot of gravitational energy density, like at the core here, the clocks move faster. So what you see, you find that this galaxy has an aged core compared to its ring. Time at this core is moving faster. This then relates to what is happening with the impossible galaxies. Only those galaxies that are compact with the high gravitational energy density, in those regions of space, time will tick faster. So that's why you end up seeing mature galaxies, because their time has moved faster than those who are not dense enough. So you find that this solves the impossible galaxy problem, because here's the equation for time. Time in a dense gravitational environment is governed by this time in a this time dark energy. Dark energy in this theory is considered as the lowest density of gravitational energy. So it will be low in low gravitational energy density, but when the density is high, the time will tick faster. The gravitational energy density, time will tick faster. And as well as the cosmological constant also varies. It also depends on gravitational energy density. If I use that equation, which I'm saying now, that's the new cosmology equation, you'll find that this is what Planck was predicting, that the matter, clumping of matter, or what is known as the sigma 8, it was predicted around these values by the early universe measurements of cosmology. Yet the late time measurements are measuring these values. And this is the region where the lambda prime model, my model that involves the Ritchie-Solerton, is predicting, and it lies comfortably within the range of the late time cosmos. So what does this model does? In the early universe, it does the same as the lambda CDM model. But as time goes on, because of the expanding Ritchie-Solerton, the lambda changes with time, and it gives the same results as those that are observed at the late time probes. They are called late time universe probes. You start finding that the same values of high value of Hubble constant is being observed. Why is the Hubble constant higher at the late time? Is because the suppression of expansion of the universe, it will appear younger than in lambda CDM cosmology. For example, let's suppose we know that a human being is, let's say, if he's 1 meter 30 centimeters, which means he's 15 years old. If he's 1 meter, let's say 7 meters, which means his average age is 40. So because of the suppressed growth in the universe under the lambda, the Ricci, so the model that contains the Ricci model, the universe appears to have not yet expanded more than it would have expect it to do under the lambda CDM. So it appears younger. So because it appears younger, the Hubble constant is larger. It's within the range of the late time cosmic measurements. And these are the values. This value here is what is measured using the lambda. I call it the lambda prime model, the one that includes the Ricci soliton. And these are the measurements in the late universe of the Hubble constant. And you will see that even the centers are in line with theory prediction, which means the lambda prime model really solves the Hubble tension, the S8 tension, and the impossible galaxies problem. It fits within the observed, within observations. So the Ricci soliton model has several far-reaching implications. It provides alternative explanation for galaxy rotation curves without the need for exotic dark matter particles, naturally explains the baronic-Talley-Fisher relation, as well as derives the empirically observed Milgram acceleration constant. It naturally predicts varying cosmological constant based on matter density, which now naturally explains local versus global differences in expansion rates, while simultaneously understanding void dynamics. So you can read in more detail for those who are very much curious on how step-by-step or more technical details on how the Ricci soliton works. I have these papers on archive. They are free to download. You can see you can copy the archive numbers. The latest one is 2504, which means this April. And the first one is in January. So you can read more technical details explaining the Ricci soliton. And I would recommend you to read the latest one, 2504. It contains more information that solves all these cosmic mysteries, a plausible solution to these cosmic mysteries, though. So thank you very much for listening to me. And I hope that my talk has aroused some curiosity in you to question what is happening in the universe. Thank you very much.
Oh, thank you very much for that wonderful and informative talk. And now we will open the floor for questions. And anyone with a question, a suggestion, a comment. So let us wait a bit for. I don't see any hand.
Can I ask a question?
Sure, sure. Thank you very much.
Dr. Marongwe, can you just give me a simple definition of a soliton? I'm not sure I really got that.
Oh, a soliton. Okay, let me talk of a soliton in real life. I mean, in which is observed. Let's suppose in the sea. You ever heard about the term of a rogue wave? A wave that suddenly appears in front of ships.
Yeah,
it moves alone. Yes. So that's called a Ricci solid. It's called a soliton. Now, a soliton is it's like a group of waves. And this wave always maintains its shape and form. Okay? It just moves, it's alone, because that's why it's also called soliton. It's alone, it moves alone, and it's like a group, a bunch of waves that make one wave that moves alone. And it can expand and grow. And the good thing about this, the funny thing about them, the solitons, even in the sea, when they clash, they can pass through each other's without noticing, without disturbing each other's. One soliton can go through the other and pass through the other. And if you notice that, this also explains what is known as the bullet cluster collision, where two galaxies are colliding, but the dark matter is not. It maintains this shape and form before and after the collision. So what is a soliton? It's like a bunch of waves that maintain their form. It's a bunch of waves, basically, that maintain their form and is very stable.
Thank you.
So, yeah, sure. So in our cosmological model, that bubble is a bunch of waves called gravitons that are interacting to form a ball. So it's a self-gravitating gravitational field, gravity that is not existing without matter. So it's a ball of gravity, pure gravity.
And you're assuming, or you know, that gravitons exist.
If you look carefully at Einstein's field equations, that the G mu nu part is actually a wave equation, and it's written G. Usually people try to interpret that G for geometry, but it's for gravitons. It's the left side is a wave equation. So, okay, let me go back to the slide and show you something. All right, so let me break down Einstein's equation in an interpretation. If we look at this part, it's a source equation. This is where this left side is waves that are being sourced by matter density. This becomes so apparently if we reduce Einstein's field equation in what is known as the weak field limit. They were just showing this G mu, this big G becomes a wave equation. This part becomes a wave equation being sourced from an energy density. So if I have to interpret it from quantum gravity perspective, the G mu nu is this blue part. It's generating high energy gravitons. That Kg, small G mu nu, is the gravitonium state. This is the Ricci soliton. The gravitons have a unique ability, like they can attract, because they are made of energy, they can attract each others. So they form a gravitonium state, a bunch of gravitons, of high energy gravitons. Only the weak ones can escape. So this is the gravitonium state. So Einstein's field equation is basically a classical wave equation. In quantum gravity, we then quantize that wave equation. So gravitons are there, it's just detecting them is weak. The only ones, the reason why gravity is weak is because the gravitonium only decays into the weak. This is where my Ricci soliton hypothesis is explaining why gravity is weak. We cannot see the quantum versions of gravitons because they are so immensely weak. It's because the high energy ones have been bundled up into the gravitonium state, leaving only the weak ones, which is difficult to detect experimentally. So yes, Einstein's field equation is a classical wave equation. Quantum gravity tries to make that wave equation a quantum wave equation. I hope that answers much of your question.
Yeah, thank you very much. Yeah.
Oh, thank you very much. I think we had a hand from Gihan.
Yes, I did put up my hand, but Stuart, I think it's a very fascinating presentation that you made. I wish I could have understood more of the the theoretical physics, astrophysics that you presented. But there's one thing that quite fascinated me, and that's the impossible galaxies that you pinpointed that JWST, through its infrared vision, has picked up for us. I don't know whether I can frame this question in a proper way, but I'll try. If it was in the 1920s, I think, that the Big Bang theory was formulated, and we arrived at a approximate time, point in time when the universe was created, was formed. And now with JWST, we've been able to get as close as possible to that original point, and lo and behold, we see old formed galaxies at a point where we didn't want to see old galaxies, but we wanted to see young growing galaxies. Okay, so you clearly explained why it's called impossible galaxies. Could it be possible? My question is that, could it have been possible that we, in the 1920s, that we made a mistake in theorizing the time frame of that origin of the universe, that it could have been much, much later, in fact, than what we thought it is? I think 13.5 billion years was what we thought. Could it have been we made a mistake?
Yes, there is a theory by an American Indian scientist, Subiru Sakar, that the universe maybe is twice as old as we imagine.
Yes.
So that's one way of seeing it. But then there are a lot of factors that mitigate it, that look like work against it. It can work from that observation, but then there are other factors that, if you include, they work against such an age. They work because we know the age of the stars. The age of the stars can tell us.
Yes.
Because maximum age, they are about mostly maximum nearly 14 billion years.
Okay.
There are a lot of factors that will mitigate. Yes, it's got that positive aspect that it can clear that problem. It says that, but then the CMB microwave radiation itself is telling us the information that contradicts that theory. It's very, and the cosmologist Subiri is a very prominent cosmologist. It means it's not a crackpot theory.
Okay.
You went through all that has to be done to do it. You can Google it, but it's not in favor. Yes, he's got arguments, but it seems like other observations seem to kill it. We want something that is smooth, that does not try to hide things that are trying to contradict it.
Okay.
We want everything to be smooth. It must be harmonious.
Yes.
Again, yes, it can try to explain that, but then other parts, it becomes in tension with measurements.
Yes.
Yes.
The actual second part to my question, again, I don't know whether I can frame this properly, but could it be that the multiverse theory could be the reason why you find impossible galaxies at a place where it shouldn't be? That these are galaxies from a multiverse.
Yes.
From another.
I've actually worked on that. There's a paper that I've actually published that shows that the maximum radius of our universe is the Hubble radius, but that's the maximum where we can see, which means there are possible other bubbles. It's like, have you seen the tiles, like the tiles in a house?
Yes.
There's a big tile, then there's another block. So that is another block universe next to our universe.
Yes.
So it's possible that some of the mature galaxies from that next door universe can turn on. So it's like neighbors' teenage sons coming into your house. Your neighbors' teenagers are coming into your house. Then you confuse them as your kids, but they are older because they are from the teenager, because they are at the edge of the fence, which means they are older galaxies.
Yes.
So they are pouring into our universe. It's a tunneling effect.
Through the black energy, dark energy forces.
Yeah, but it's like a quantum tunneling effect, like in quantum phenomena, where a particle can go through a barrier, and it's like an exchange of galaxies between universes. That's possible. I've actually worked on that. That's possible.
Okay.
Yes. From a quantum gravity perspective, that's possible.
It
those
can
old
be
galaxies are coming from a neighboring galaxy. It's possible, highly likely.
A neighboring universe.
Yes, they could be coming from a neighboring universe.
Yes.
And one way of actually finding that is to keep on looking. When we observe a galaxy that was not there before, then we know they are turning in. But this has happened with stars, actually. There's what's called a pan survey. They've been looking at stars since photography of stars began. Then they're seeing some stars that are appearing and disappearing without trace. Where are they coming from and where are they going? You can Google that. There's actually a Swedish group of scientists that are actually accumulating data on those, a database on those stars that suddenly appeared and then suddenly disappeared. No explosion, no nothing. And some that just appear from nowhere. There was no star, then suddenly there's a star. So it could be possible they're coming from another universe, tunneling into ours. The universe is full of mysteries, as you can say. We cannot fathom what is happening.
No. We are still scratching at the surface of knowledge there.
Yeah, obviously. We are still infants in terms of knowledge. Yes.
Fascinating story.
Oh, thank you very much. Any other question? Any other question?
Maybe I should just add on to my latest, the April paper. I've been getting emails from cosmologists, some prominent cosmologists, finding that work very interesting, because it not only explains what dark matter is and what dark energy is, it solves the SA tension and the Hubble tension at the same time, smoothly, without some tensions, just harmoniously, with very small parameters. So I have received an email from one prominent Russian cosmologist. I think he completed his PhD when I was born. That's amazing. He completed his PhD when I was born, like 1970s, you see. So imagine someone that well versed in that field for those years, for nearly 50 years. Yes, he has contacted me. It seems it's very impressive indeed.
Congratulations. You made some references to two archives of your papers. How do you just copy those those symbols onto Google search?
Onto Google search, yes. Just copy those numbers onto Google. Have you seen them? Have you copied them?
Dr. Sipa, will you be sending the recording soon, right?
Oh yeah, sure.
Oh, yes.
They are there.
Yeah, then I can get it from there.
Yes, just look at them. They are very interesting.
Yes.
Sure.
Would you? We have your email address as well. No, I don't think we have your email address. Maybe along with the recording, I'd like to send our listeners, our members, your email address if they want to ask you some questions. I'll get it from Dr. Sipa. I'll get it from Dr. Sipa. Yes.
Yes, sure.
All right. Any other question? No, let me thank the speaker, Stuart Marongwe. His theory, the way I see it, is has got a lot of potential, and we have already have had several students here in the university doing a project on his theory, and we still have more will be. So we really thank the speaker for his talk, and also for the fruits that is availing to the younger generation. Thank you very much.
Thank you,
Let me
Stuart.
also, thank those who managed to log in and be present with us, and those who didn't manage, they will see the recording. We all have challenges in life at different times. I will give Gihan maybe a chance to say a final word. Thank you very much, everyone.
Sure. Thank you very much,
Stuart.
everyone. Thank you.